Hi everyone and welcome to MathSux. This video is going to help you pass the Algebra 2 Common Core Regents. We're doing this one question at a time. Here is question 25 with part 2. Describe the translation that maps f of x equals log of x to g of x that equals log of x plus 3 minus 5. So we're saying we're translating this log of x to this g of x log of x plus 3 minus 5. So what's going on? What did we do to this original function basically? So we started with log of x and then we transformed it to log of x plus 3 minus 5. So what's the difference here, right? We have this horizontal shift where we're going left 3 units. So whatever this sign is positive, so we know we're going to be going to the left. We're always going to do the opposite when it comes to the horizontal shifts. We also subtracted this 5. We also are doing a vertical shift down 5 units because we're subtracting. So that's really all we need to write here is left 3 units and down 5 units. So this is all you need to write. I just wrote all this out so we have a clear picture of before and after and what's going on here. But that's our answer. Question 26. Solve algebraically for x, where 1 over 2x minus 5 sixths equals 3 over x. So first thing I'm going to want to do is just rewrite this. So the first thing we want to do is get everything to be the same denominator. We're going to need the same denominator. So to do that, we're just going to look at this and see that we should get 6x as the common denominator. So to get 6x on the denominator over here, we're going to have to multiply the numerator and denominator by 3. And this will give us 3 over 6x minus, to get 6x here, we'll have to multiply numerator and denominator by x. Get 5x over 6x, and then over here just multiply by 6, right? So 6 times 3 is 18, and then this is over 6x. And now since this is all the common denominator of 6x, we can actually just drop it and we'll get 3 minus 5x is equal to 18, and then we could just solve this as a normal easy algebraic problem. So and we get x is equal to negative 3, and that's our answer. Question 27. Cosine of theta is equal to negative 2/7 with theta in quadrant 2. So let me just first sketch this out. And it says it's in quadrant 2, so just a reminder of the quadrants. We have quadrant 1, 2, 3, and 4. And here I'm just labeling each quadrant and what's positive. So here all the trig functions are positive. Here just sine is positive, tan is positive, and cosine is positive. So we're saying cosine of theta is in quadrant 2, negative 2/7. We know it's over here somewhere. Find the exact value of sine of theta. So already we could see we know sine of theta is going to be positive because it's in that quadrant 2. So we know our answer will be positive. So how are we going to find this? We're going to use one of the identities. Cosine squared of theta plus sine squared of theta is equal to 1. And then using this, we can plug in what they gave us over here. They say cosine of theta is equal to negative 2/7. So we know we can plug in negative 2/7 squared, because that's what cosine of theta is equal to, plus sine squared of theta, which we're trying to find, and set that equal to 1. This is going to be 4 over 49, just squaring the numerator and denominator, 2 squared over 7 squared. So we get sine squared of theta is equal to 45 over 49. So remember, this is a squared, so we want to take the square root of both sides. So we get sine of theta is equal to radical 45 over radical 49, which is 7. And we could actually reduce this more because we want the exact value of sine of theta. So let's reduce this even more. 45 can be broken down to radical 9 and radical 5. So this reduced is going to be 3 radical 5 over 7. And that's our answer. So sine of theta is equal to 3 radical 5 all over 7. And we know remember it's positive because it's in that quadrant 2. Question 28. Given a is greater than 1, use the properties of rational exponents to determine the value of x for the equation below. We're going to rewrite this numerator as a to the 10 over 5, which you can see is going to be a to a squared, right? But we're going to leave that for now, and we're going to rewrite this as well. So this denominator, a cubed raised to the 1/2, you could see that we can multiply these and get a to the 3/2. So simplifying this further, and we're going to set this equal to a to the x. Simplifying this further, a 10 raised to the 10 divided by 5, we can just put a squared over a raised to the 3/2. And now we can subtract these. So if we did a raised to the 2, and we bring this, since these are the same base, they're both a, we can subtract the exponents. That's the exponent rule. So we do 2 minus 3 over 2 is equal to a over x. And remember the rules for subtracting fractions, we want to get the same denominator. So we're going to multiply this times 2 over 2. So we'll get a raised to the 4 over 2 minus 3 over 2 equals a to the x. And then 4 minus 3 gives us 1, and then that denominator will remain the same when subtracting fractions. So we get a to the 1/2 is equal to a to the x. And then now you could see our exponent x is equal to 1/2. And that's our answer. Question 29. Graph at least one cycle of y equals 5 sine of 4x minus 3 on the set of axes below. So I'm just going to bring this down so we can look at it and label it y equals 5. Okay, so the first thing I notice here is that this is a sine function. So sine functions, remember, have that S curve starting at 0, 0, where it looks something like this. But this isn't that simple, right? This has all these other numbers happening here. So let's do this kind of transforming it one step at a time. So if we have this amplitude, this is the amplitude 5. That's kind of like the height of the graph. So here in a simple sine of x, the maximum is 1 and the minimum is -1. But when there's an amplitude of 5, now the max and min are going to be 5 and -5. So we still have, we're starting at 0, 0, but now the highest point of this sine graph is 5 and the lowest is -5. So something to keep in mind. So another thing we have here, I'm going to skip this for x for now. Another thing we have here in the end is a vertical shift down 3 units. So we're going to transform our mini graph down here one more time. So transforming this one more time. And now instead of starting at 0, 0, because we're shifting the entire graph down 3 units, we're actually going to start at -3. So this is going to be like our new baseline. So here before 0 was our baseline, and now it's going to be -3. And this is also going to affect the max and min of our graph. So before our max was 5 because of the amplitude, but now we're going to be shifting this entire graph down 3 units. So 5 minus 3 will give us 2. So our highest point will be at 2 now, 2. Our lowest point is going to be -5 minus 3, which is -8. So this is like our baseline, -3. Our max is 2 and our min is -8. And we got that by having the amplitude and then subtracting 3 to get the max, and then taking the min and subtracting 3 and getting minus 8. And notice our sine curve, instead of starting at 0, starts at -3 and then ends at -3. So this is just kind of like a roadmap for us to use, but we're still missing one more piece of information. We also need to look at the frequency. So this right here is the frequency, which is equal to 4. So the frequency, just a reminder, represents the number of cycles of this sine curve that are going to happen between 0 and 2 pi. That means there's going to be 4 cycles of this graph happening between 0 and 2 pi. But if you look up here, they said they just at least once. We don't need to graph all of them, we just need one. To find the length of one cycle, which is what we need to graph, we need to find the period, which we find by doing 2 pi divided by the frequency. So we're doing 2 pi divided by 4, which is equal to pi over 2. So that means one cycle happens between 0 and pi over 2. So now we have everything we need. We're going to be ending at pi over 2. So that means if we do, to find out what values to put for the x, pi over 2 is equal to 90 degrees. So we're just going to do 90 divided by 4. So we're going to be counting by 22.5 degrees and converting this into radians. So 22.5 divided by 180 is 1 over 8. So we're going to get to pi over 8 here. So over here is pi over 8, and then 22.5 plus 22.5, 45 degrees, which we know is pi over 4. And then if you added another 22.5, you'll see you get 90 degrees, which is pi over 2. So now we can graph this, and remember we're going to use this little roadmap we made. So remember we're starting at -3, and then this is our baseline. We're going to go up to our max, which we found earlier. We're going to go back down to our baseline at -3. Then we're going to go down all the way down to -8, our minimum. 1, 2, 3, 4, 6, 7, 8. And then we're going back to our baseline at -3. And then we just need to connect all our points. So remember, this is our baseline -3 because of our vertical shift down. Our max is 2 because we had an amplitude of 5 and we had a vertical shift down. And then down here is -8, which was originally -5, but then we brought it down 3 units for that vertical shift. And that's our answer. Question 30. The cost of a brand new electric hybrid vehicle is listed at $33,400, and the average annual depreciation for the vehicle is 15%. The car's value can be modeled by the function v of x is equal to 33,400 times 0.85 raised to the x, where x represents the years since purchase. Julia and Jacob have each written a function that is equivalent to the original. And then they have Jacob's function and Julia's function. Whose function is correctly written to reveal the approximate monthly depreciation rate? Justify your answer. So this question is kind of confusing. If we look back here, this is our original equation that they give us. V of x is equal to. So this is our original, and they're saying that these two are equivalent to the original. And they're looking for the monthly, rewritten it correctly to reveal the approximate monthly depreciation rate. And if you look back the original, it says has the annual depreciation rate. So this is the annual, the yearly, right? But they want the monthly depreciation rate. So our goal that we're looking for is to have monthly depreciation rate. So basically, we want to adjust the rate. We're going to need to have 1/12 exponent within the parentheses. So just focusing on the rates, we have the original rate, original yearly rate is 0.85, right? That's what this represents. This is the original equation, and then this is the rate if we know our exponential and depreciation functions. So this represents the rate, and now we need to find the monthly rate, which would be 0.85 raised to the 1/12. So if we do 0.85 raised to the 1 divided by 12, we end up getting 0.98654. We end up getting this, which you can see matches Julia's function, right? This rate is raised to the 1/12, and then all of that is raised to 12x to represent the yearly, because right, they said these are equivalent to the original. These two functions are equivalent to the original. But meanwhile, this rate within here represents the monthly depreciation rate. So Julia is our answer. And that's our answer. Question 31. Write a recursive formula for the sequence 8, 20, 50, 125, 312.5. So I'm just going to rewrite this. So first let's see if this is a geometric sequence or an arithmetic sequence. So it looks to me like it's geometric. Let's do 20 divided by 8. And we get 2.5, so we know we're multiplying times 2.5 here. And let's see if that pattern keeps going. 50 divided by 20. So again, you could see we're multiplying each number by 2.5. Okay, so we know this is a geometric sequence where R, the common ratio, is equal to 2.5. So, okay, so now we need to write a recursive formula for this. So the geometric sequence formula looks something like this. A sub n is equal to a sub 1 times r to the n, where a is the first term, which you could see is equal to 8. R, the common ratio, that number we're multiplying times each number, we already stated is equal to 2.5. And then n is just the term number and within the sequence. So if we're going to write a recursive formula, there's a special notation where we need to write this. So we always write it in two parts. So the first part is we label the first term a sub 1, the first term, which we said is 8, and then we had to give our formula. So this is a sub n, and then we're kind of just plugging in what we found up here. So a sub n is equal to 2.5, that common ratio, times the previous term. So with recursive formulas, we're always multiplying the previous term. So to show that, we always do a sub n minus 1. So it's like n is our term number, and it's the previous term, the value of the previous term. So this is our answer. And you can always check it too. So you can actually check the formula we just wrote. So if we did our first term is equal to 8, and then the next term, a sub 2, would be 2.5 times 8, which is that previous term, which we know will give us 20. And that's the next thing in our sequence. We found the next term, it would be 2.5 times the previous term again, which this time is 20. And we're just plugging in, see, the previous term. 8 was the previous term here, and we're plugging it in. And then 20 is the previous term here, and then we're plugging it in. So 20 times 2.5 is equal to 50. And you could see how this pattern keeps going. And that's our answer. Question 32. A grocery store orders 50 bags of oranges from a company's distribution center. The bags have a mean weight of 3.85 pounds per bag. The company claims that their bags of oranges have a mean weight of 4 pounds. The grocery store ran a simulation of 50 bags 2,500 times, assuming a mean of 4 pounds. The results are shown below. Is the mean weight of the grocery store sample unusual? explain using the results of the simulation. The grocery store sample, they said the mean weight was 3.85. And now, using the simulation, we're going to find the 95% confidence interval. So the 95% confidence interval will tell us if this number is unusual or not. And if it falls outside of it, then it's unusual. If it falls inside that interval, it's not unusual. So to find the 95% confidence interval, we're going to do mu plus or minus 2 times the standard deviation. Be careful here because there's two mu's, there's two means, right? There's the mean in the simulation and then there's the mean of the grocery store. So this is the grocery store mean, but we're going to be doing the simulations mean and standard deviation over here. So these are the simulation results. And that's what we're going to be using when plugging into this 95% confidence interval. So the mean here is 4.001 plus or minus 2 times 0.026. So now we're going to find two values. So there's going to be the bottom of this interval for minus 2 times 0.026, which gives us 3.949. So that's the bottom part of this interval. And then the top part, we're going to plug in the same thing. And instead of a minus sign, we're going to put a plus sign. And this goes up to 4.053. So now, if you look back at our grocery store sample, the mu over here, 3.85, we have to ask ourselves, does 3.85 fall within this range? And no, because you can see the bottom, the minimum value of this range is 3.9, and this goes below that. So what we're going to answer here is that this is unusual. So yes. So our answer here is yes, it is unusual because the mu 3.85 found at the grocery store falls outside the 95% confidence interval. And that's our answer. So this is the end of part 2. Look out for part 3 coming out soon. Good luck and happy calculating. Need more practice? Check out MathSux.org for more questions. Link below. Also, don't forget to subscribe. Happy calculating!